Another aspect of the heating and cooling system is the chilled beams. And we use chilled beams in the laboratory areas as well as the office areas. And the thing that I love about chilled beams is that it uses air, but we use once through air. That is, there's no air that's recirculated through the building. Air comes in through an air handler into the chilled beam and then it's exhausted out of the building. So everybody in the building is always getting fresh air. The other thing that chilled beams take advantage of is that water is the medium for providing the heating and cooling. And so we have water that goes through the chilled beam, hot water or cold water, so that chilled beam can do heating or cooling. Well, water is much more dense than air. It's 3,500 times more dense than air when we talk about the heat carrying capacity. So we can have very small 1-inch pipes or we can have a 20-inch duct. And when I talk to the architects about which one they would prefer, the answer is obvious. I like the 1-inch pipe because the pumping energy is 7 times less than the fan energy to deliver the same amount of heating and cooling. So the chilled beams do require air, that is the ventilation air, but it's just enough air to make us healthy in the building. So our ducts are 1/3 the size of what they would have been if it was a traditional air conditioning system and we don't have the recirculated element that we would have in normal offices. So the airflow strategy in the laboratories is one where we, again, bring in 100% outside air, fresh air, and then exhaust it. In labs, we do that for safety. You don't want to recirculate laboratory air, especially if there's a spill. So what we do is we look at how much air do we need, and a lot of labs, and labs are very big in San Diego, San Francisco Bay Area, where the whole biotech industry, this is a big area, and there's a lot of laboratories and universities all over the US. There hasn't been a lot of thought until recently of what's the right amount of air to move through a laboratory. And it used to be rules of thumb would be somewhere between 6 and 12 air changes per hour. So when we were designing this building, we looked at the state-of-the-art research. What were people finding is an effective amount of air and at the same time would protect people's health. And as it turns out, the laboratory air is designed to evacuate fumes from a spill. So if we have 8 air changes per hour or 6 air changes per hour, which is a somewhat typical number, or even 10 or 12 in some buildings, that's all designed to accommodate a chemical spill. Well, how often do we have chemical spills in labs? They do happen, and we have to be ready for them. But it's 99.99% of the time there's no spill.
And there really isn't, a basis for those numbers, except that people have been using them in the past and they know they work. The problem is they come with a huge energy penalty. And so what we did is worked with the Venture environmental safety and health people, and went through a process of saying, okay, what air change rate can we drive this down to and still be comfortable? So this building is designed to have an unoccupied air change rate of 2, occupied of 4.
And we also put in a sniffing system, a system that pulls air samples of the lab and it measures the air, and if there's a spill, it can see that, and then the air can get ramped up to 8 air changes per hour when there's a spill. So we're providing optimized safety at the lowest possible energy. And that was the basic strategy, and I think it's one that's really caught on in laboratories for research at universities, and it's slowly but surely making its way into industry, biotech industry, and pharmaceuticals.